Welcome to How to Succeed in ECE Without Really Trying. I'm Dr. Linda DeBrunner, and in this video, I introduce the concept of ideal amplifiers.
So an ideal amplifier can be defined to be a device whose gain is constant over all frequencies omega. Okay, so this would be ideal for sure. And here's a picture of that model. So we would have a source with a source resistance, and then we'd have the actual amplifier we're talking about, and then we'd have some kind of a load. And I've shown this load to be resistive. Okay, for this particular ideal amplifier, we will define the frequency response, h of j omega, to be V out of j omega over Vs of j omega, and that we will call G. So we can look at this model and use KVL. So if we apply KVL on this first loop, the input side, we get minus Vs of t plus IRs plus I times Rn. I guess I need to define that. Rn equals 0. Okay, let's go over that again. Minus Vs plus IRs plus IRN equal to 0. When we solve for Vn in terms of Vs, what we would end up with is an equation for our voltage divider. So we actually derived this equation earlier, but you could readily evaluate it by just using KVL. On the output side, we can do the same thing. Now notice that I've shown a dependent voltage source that's controlled by a value A, and we don't need to define A at this time. We'll just say that that's what it is. And A is going to be multiplied by the input. So that's just saying that this voltage source, a dependent voltage source, will be A times Vn, where Vn is that voltage there, where and A is a constant. Okay, so when we write that loop, we get minus AVN plus IR out plus IRL. And you can solve for V out and Vn. We get V out is equal to A times Vn times RL over R out plus RL. And that again is just a voltage division, and we can solve for that. We can put this together to get V out over Vs to be equal to A times Rn over Rs plus Rn times RL over RL plus R out. If we define G to be V out over Vn, not V out over Vs, but V out over Vn, we end up with A times RL over R out. And the reason we want to define the gain in this way is because the source resistance is not due to the is actually associated with the input source, and the loss across it is not because of the amplifier. Now, this result has got some bad aspects to it, okay? First of all, the gain depends on the load, okay? And that's not good. We would like to have a gain that's independent of the load, okay? Also, the gain relates Vn to V out, not to Vs, and ideally it would relate it to Vs. But if we let R out be much less than RL, okay, so R out would be the resistance looking into the back end of that amplifier, and if it's much less than RL, and if the input resistance is much greater than RS, then we can do some evaluation. Okay, so if we let R out go to 0, again, it has to be much less than R out, but if we let it go to 0, then the limit of RL over RL plus R out as R out goes to 0 will be 1. Okay, this means that G is going to be approximately equal to A. If we let Rn go to infinity, again, remember Rn has to be much greater than Rs based on our assumptions. If we let Rn go to infinity, then the limit of Rn over Rn plus Rs as Rn goes to infinity also goes to 1. And that means that Vn of t will be approximately equal to Vs of t. Now we can talk about what makes a good amplifier. So we could say a good amplifier has a couple of characteristics: a small output impedance and a very large input impedance. And these two characteristics can be measured. Okay, the input impedance will be equal to the ratio of Vn over In. And the output impedance, again, is going to be the Thevenin resistance looking back into the circuit from the right side. So that's VOC over I short circuit.
These are the characteristics of an ideal amplifier.